Now we'll begin this chapter, Gauss divergence theorem. This is most important topic of the vector calculus, Gauss divergence theorem. See, the theorem says, suppose V is the volume bounded by a closed piecewise smooth surface S. Suppose you have V is the volume bounded by a closed piecewise smooth surface S. This is the surface S. The surface would be closed. It talks about the volume enclosed by a closed piecewise smooth surface S. Now f is a vector function. This is a vector function which must be continuous. This is very important. This must be continuous at each and every point which lies inside S. Each and every point which is there in the volume V enclosed by S, and it should be continuous and should have the continuous first partial derivative. This particular function f must be continuous at each and every point in V and should have continuous first partial derivative at each and every point. Only in this case the surface integral of f over the surface S is equal to the volume integral of its divergence over the volume, right? So surface integral of f, that is also called flux of f across S. The flux of f across S is equal to the volume integral of its divergence over the volume V which is enclosed by S. And mind it, n, what is n over here? N is the outward drawn unit normal vector to S. Suppose I take this as ds, then at any point you have two normals, n and this side also n. One is outward drawn. Outward means outward from the volume V. Outward from the volume V. So this is your n. This is not n. This is not n. N is an outward drawn normal. Over here, n is an outward drawn normal. In this Gauss divergence theorem, n is an outward drawn normal. So the condition is f must be continuous and should have continuous partial derivative at each and every point inside S, that is at each and every point in V. In that case, the surface integral of f over the bounding surface is equal to the volume integral over V of its divergence, right? N is an outward drawn normal. Outward means outward from the volume. So this is the Gauss divergence theorem. Now we will consider a question on it. Let us see this question. Use Gauss divergence theorem to evaluate x3y dy dz plus x square y dz dx plus x square z dx dy, where S is the sphere x square plus y square plus z square equal to 1. This is a sphere having the center at the origin and radius 1. So let us first draw this. So we can draw this. So this is the sphere. We have to evaluate it on this sphere. We can draw the coordinate axis also. So this is coordinate plane. Now we have to evaluate this Gauss divergence theorem. We have to evaluate the surface integral over this sphere, over the surface of the sphere. See, first of all, before using Gauss divergence theorem, I have to reduce this. I have to write this in terms of f dot nds. Once I get f, only in that case I will be able to get its divergence. So I must write it in this form. So here I will tell you about how we can write ds. See, this nds can be written as dy dz I plus dx dz j plus dx dy k. Alright, I'll show this how we can write this. I'll show you in the figure. I'll rub this figure. I'll show you in the figure how we can write this. See, sometimes in some books you will find that this is also written as ds vector. So ds vector is just nds. Any vector can be written as the magnitude into the unit vector in that direction. So n is the direction of this ds vector. So this surface element vector can be written as dy dzi plus dx dzj plus dx dy k. I'll show you how I can write this. Let me draw a separate figure. this is ds, this is ds, so this is your ts and this is n. So this ds, when I take projection on xy plane, this gives you dx, this gives you dy. When I take projection on yz plane, this gives you dz and this gives you dy. When I take the projection of ds on xz plane, then this gives you dz and this gives you dx. Now for dx dy, the direction lies in k direction. Over here the direction of surface lie, dy dz surface lie in I direction, and over here the direction lies in j direction. So you find that these dx dy, dy dz and dz dx are just the component of ds. It is just a component of ds. So I can write this nds as the component of xy plane, that is dy dz I, the component on yz plane, that is dy dz, sorry, this is not, this is dy dz, I component lies in this direction, right? So this is dy dz I, then the component in j direction lies in xz plane, so this is dz dx j, and the component of this component lies in k direction, that is dx d by k. So this is nds. Now I can write this integral I as simply xqi plus x square yj plus x square zk dot nds. Now we'll apply. Now you find that this particular function is continuous and having continuous partial derivative at each and every point inside the sphere. So I can very well apply Gauss Divergence theorem. This is your f, this is just your f dot nds. So f over here is xqi plus x square yj plus x square zk. So this will be equal to del dot f d tau, or d tau can be written as dx dy dz, and del dot f will be 3x square plus x square plus x square, which comes to be 5x square dx dy dz. So we have to evaluate this in the volume enclosed by the surface, that is surface is sphere. So I'll use spherical polar coordinate where x is simply r sine theta, x in spherical polar coordinate x is r sine theta cos phi. So this will be r square sine square theta cos square phi, and dx dy is written as r square sine theta, I write d phi d theta dr. So first of all I will integrate it with respect to phi. So it is 0 to 2 pi, and cos square phi d phi from 0 to 2 pi will be equal to pi. You remember that all these integrals, these are famous integrals. 0 to 2 pi sine square phi d phi is pi. You can use Gauss function also. So this will be r4, and this will be sine q theta, sine q theta d theta from 0 to pi, and this is 0 to 1. Alright, so this is nothing but 10 pi 0 to 1 r4, one more integral, 0 to pi by 2 r4 sine cube theta d theta. Now I will use Gauss function. I love this part. So I can use Gauss function in evaluating these integrals. So this will come as sine cube theta is going to be, this is 10 pi. See, it is, we have used this 0 to 2a fx dx is 20 to a fx dx if f2a minus x is fx. So it is followed over here. Sine cube theta d theta 0 to pi is basically equal to twice of 0 to pi by 2 sine cube theta d theta. So this is 0 to 1, and sine cube theta will be integrated as, I write this over here, sine cube theta d theta 0 to pi by 2 will be 3 plus 1 by 2, that is 2, 1 by 2, and twice of 3 plus 2, 5 by 2. I am using gamma function. You must know what is gamma function. You must revise the chapter of integral calculus before doing this chapter. So it is 10 pi. This is 10 pi into 1 gamma 1 by 2, 2, 3 by 2, 3 by 2, and 1 by 2 gamma 1 by 2. This will cancel out, and this will be r4 dr. So r5 by 5, that is 1 upon 5. So finally what you will get is, finally you get 4 pi upon 3. This is 4 pi upon 3. So this is how this problem can be done. We